Hello there, and welcome to the Sleepy Science Channel. I'm so glad you're here. Maybe it's been a long day. Or maybe you're the kind of person who likes to fall asleep wondering about time, gravity, and the deep silence between galaxies instead of counting sheep. Either way, tonight's journey is for you. You don't need to do anything now but rest. Let your breath slow, your thoughts soften, and your body grow quiet, as if you're already floating far from Earth, beyond the stars, where space expands in every direction. Because tonight, we're going to drift gently into the far future of the universe. Not in a straight line, but through slow cosmic chapters, from dying stars and fading galaxies to the long, cold silence that may lie beyond them. A story told not in endings, but in entropy, in distance, and in the quiet settling of all things. From black dwarfs and evaporating black holes to time itself losing meaning, this is a journey into the stillness that waits at the edge of everything. We'll go slowly, gently, just one sleepy thought at a time. And just before we begin, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. When we look up at the night sky, it's easy to feel like everything is permanent. The stars shimmer in familiar patterns. The moon returns in steady cycles. But this stability is an illusion of scale. On cosmic timescales, everything is in motion, not just through space, but through time. The universe is not a static backdrop. It is aging. And like any aging system, it is slowly changing in ways we can begin to measure and even predict. The most immediate sign of this aging lies in the redshift of distant galaxies. As light travels through expanding space, its wavelength stretches, moving toward the red end of the spectrum. This means that the farther a galaxy is from us, the more its light is redshifted, a clue not just to distance, but to time itself. Galaxies are not simply moving away. The space between us is growing, and with it, the universe is cooling and diluting. This redshift is a whisper from the past, but also a glimpse into the universe's future. Cosmic background radiation is another gentle indicator of age. This ancient light, left over from when the universe was just 380,000 years old, now fills the cosmos as a faint microwave hum. When it first emerged, it glowed brightly at thousands of degrees. Today, it has cooled to just a few degrees above absolute zero. And it continues to cool. Over billions of years, this fading radiation tells us something simple but profound. The universe is getting colder. The warmth of the Big Bang is still with us, but only as an echo, stretched thin by time. Stars too are aging, both individually and collectively. Our Sun, for example, is about halfway through its main sequence lifespan. It fuses hydrogen into helium, shining steadily for billions of years. But stars are finite machines. They require fuel, and once that fuel runs out, they change. Some swell into red giants. Others collapse into dense remnants. This process is not unique to our Sun. It is happening everywhere. Slowly, the number of new stars being born is decreasing. The great galactic nurseries are winding down. Galaxies, in turn, are evolving. In the early universe, galaxies were chaotic and active, colliding and merging frequently. Today, many are more settled, less luminous, and less dynamic. Spiral galaxies like the Milky Way still birth stars, but at a lower rate than in the past. Elliptical galaxies, once formed from cosmic mergers, now lie quiet and red, with little gas left for star formation. Over time, more galaxies will grow dim. Some will be swallowed by black holes. Others will simply fade into the background, drifting ever farther from their neighbors. All of this points to a deepening stillness. As time stretches forward, the universe's energy becomes more diffuse. High-energy phenomena become rarer. The cosmos trends toward equilibrium, a state in which no usable energy remains to drive change. This idea, known as the heat death of the universe, suggests a far future where everything is cold, still, and inert. It is not a sudden end, but a quiet one, a fading, a cooling, a long cosmic exhale. And while that future lies trillions of years ahead, its roots are already visible in the sky tonight. If we could tune our vision to microwaves instead of visible light, the night sky would glow with the afterimage of the Big Bang. This is the cosmic microwave background, the oldest light in the universe, released when matter and radiation first parted ways nearly 14 billion years ago. It once blazed in visible light, but has since stretched into microwave frequencies as space expanded. What we see today is a faint, uniform glow at just under 3 degrees above absolute zero. And it is still fading, stretched thinner with every passing eon. Over time, the universe will become more and more transparent. As the cosmic background radiation cools, its photons lose energy and slip below the threshold of detectability. Eventually, they will have wavelengths so long that they become effectively undetectable, smeared thin across vast stretches of empty space. The last whisper of the Big Bang will still exist, but as a background too faint and too cold to register, even for the most sensitive instruments. The universe will still contain this ancient memory, but it will become functionally silent. At the heart of this fading lies a simple truth. The universe is governed by the second law of thermodynamics. This law tells us that in any closed system, entropy, a measure of disorder or energy dispersal, will tend to increase over time. The cosmos, though not entirely closed in the traditional sense, behaves in ways that mirror this rule. Energy that once fueled stars and galaxies is gradually spreading out, becoming less concentrated, less usable, and more evenly distributed across space. Entropy does not mean chaos in the colloquial sense. It means that energy is becoming less able to do work. A hot object in a cold room can warm its surroundings. But once both reach the same temperature, no more heat can flow. On a cosmic scale, this is what aging looks like, a trend toward thermal equilibrium. The universe, once full of sharp temperature differences, is smoothing out. Galaxies, stars, and even particles are drifting toward a state where no energy gradients remain. This directionality, from order to disorder, from usable energy to entropy, gives time its arrow. The reason we remember the past but not the future, the reason stars shine and black holes form, is because entropy increases. The expansion of the universe helps drive this increase by spreading energy out over larger and larger volumes of space. With every tick of the cosmic clock, the total entropy rises. The universe is not just expanding in space, but deepening in time, moving irreversibly toward a colder, flatter state. Eventually, all heat will be so evenly distributed that no more movement will be possible. No more stars will shine. No more machines, biological or mechanical, will function. And yet, even in this final stillness, the entropy of the universe will be maximized. It is the quietest possible outcome, a cosmos not torn apart or crushed, but simply settled. Not dead in the dramatic sense, just done. Not a sudden ending, but the slow fulfillment of a long, entropic journey. To understand how the universe might end, we first need to stretch our imaginations across unimaginable spans of time. The current age of the universe is around 13.8 billion years, a number that already defies intuition. But if the universe continues expanding as expected, it could persist for hundreds of trillions, even quadrillions of years. These durations are so long that all known stellar activity, all galactic mergers, and even the evaporation of black holes will take place early in comparison. Over the next few billion years, galaxies like our own will continue forming stars from the gas and dust that remains. But this fuel is finite. Star formation rates have already declined dramatically since the universe's peak period of stellar birth, about 10 billion years ago. In perhaps 100 trillion years, the last star will flicker into darkness. What follows is the so-called Degenerate era, a time when white dwarfs, neutron stars, and black holes drift silently through space, remnants of a brighter cosmic past. As this era unfolds, these compact objects will cool, collide, and occasionally interact, but activity will be rare. Over even longer timescales, stretching into 10 to the power of 100 years or more, even protons may decay, depending on the laws of particle physics. If proton decay is real, then all normal matter, atoms, planets, the remnants of stars, will eventually disintegrate into subatomic particles. If not, matter will still decay in more exotic ways, through quantum tunneling and gravitational interactions. The long, slow cooling of the universe leads toward a concept known as heat death, not an explosive ending, but a terminal settling. In this scenario, the universe asymptotically approaches thermal equilibrium. All temperature gradients flatten out. All usable energy is expended. No stars shine. No structure changes. No work is done. It is a state of maximum entropy, where the cosmos contains energy, but none of it can be harnessed to create change. Everything continues, but nothing happens. This is one of the most widely accepted possibilities for the ultimate fate of the universe. Unlike a dramatic collapse or explosion, heat death is quiet, absolute, and eternal. It is driven by the same rules that govern why coffee cools in a mug or why stars run out of fuel. But here, those same rules apply to everything, on every scale, for all of time. And while this outcome lies far beyond anything we can witness, it follows directly from what we already observe in the sky. So the next time you see a star, remember that it is burning fuel, creating order at the cost of increasing entropy. It is a temporary flare of complexity in a universe whose long-term direction is downward, towards simplicity, stillness, and silence. In this way, cosmic aging is not just about time passing, it is about the deep physics of how time works. And as we move forward, we will follow this story from stars to atoms, from galaxies to black holes, tracing each step toward the end. To understand the long future of the cosmos, we must first understand its luminous engines, the stars. Every star we see in the night sky is a complex thermonuclear furnace, balancing the inward pull of gravity with the outward pressure of radiation. This delicate balance defines a star's main sequence phase, where it spends most of its life fusing hydrogen into helium. The Sun is in this phase now, quietly burning through the fuel at its core, shining with the steady light of equilibrium. Hydrogen fusion is the simplest and most efficient nuclear reaction in the universe. It powers stars for billions of years, depending on their mass. Smaller stars burn fuel slowly, living for tens or even hundreds of billions of years. Larger stars are brighter and hotter but live much shorter lives, racing through their hydrogen supplies in just a few million years. But no matter the size, all stars eventually face the same fate. They run out of fuel, and the balance that held them together begins to fail. As hydrogen becomes scarce, the star's core contracts under gravity, heating up in the process. In many stars, this leads to a new phase, the red giant stage. The outer layers of the star swell outward, often expanding to engulf nearby planets, while the core continues to fuse heavier elements like helium and carbon. This stage is unstable and temporary. The star's structure becomes layered and dynamic, with fusion occurring in shells around an increasingly dense core. Eventually, even these fusion reactions can no longer continue. The way a star dies depends entirely on its mass. Small to medium stars, like our Sun, shed their outer layers into space, creating glowing planetary nebulae. The core that remains becomes a white dwarf, a dense object roughly the size of Earth but with the mass of the Sun. These stellar remnants no longer undergo fusion. They glow faintly with leftover heat, slowly cooling over trillions of years until they become cold, invisible black dwarfs. None yet exist in the universe, because not enough time has passed. Heavier stars end their lives more violently. When fusion stops in a massive core, gravity wins completely. The collapse is sudden and catastrophic, resulting in a supernova, an explosion that can outshine an entire galaxy for a brief time. What remains after the blast depends on the original mass of the star. If it was heavy enough, the core becomes a neutron star, an object so dense that atomic nuclei are crushed into a sea of neutrons. These stars are only about 20 kilometers wide, yet they can weigh more than the Sun. In the most extreme cases, even neutron degeneracy cannot hold back gravity. The core collapses further, forming a black hole, a region of spacetime where gravity is so intense that nothing, not even light, can escape. Black holes do not shine. They do not radiate, at least not in the traditional sense, but they persist. And they are now considered likely to be the last surviving structures in the universe. From soft starlight to violent collapse, the fate of every star sets the stage for what the universe becomes. Star formation is not an eternal process. It depends on the presence of cold hydrogen gas, the raw material that gravity condenses into new stars. Over cosmic time, galaxies have drawn from large reservoirs of interstellar gas to create generations of stars. But this supply is finite. With each star that forms, a portion of that fuel is permanently locked away. Some is returned through supernova and stellar winds, but not enough to replenish what was consumed. Slowly, the galaxies are running dry. Already, the universe is well past its peak in stellar birth. That peak occurred more than 10 billion years ago. Since then, the rate of star formation has declined by more than 90%. Large galaxies like the Milky Way still form stars, but more slowly than in the past. Smaller galaxies and gas-burst systems are nearly dormant. Eventually, perhaps within 100 trillion years, the last of the interstellar hydrogen will be gone, and the final star will be born. After that, the universe enters a new phase. This future era, sometimes called the Degenerate era, will be one of deepening stillness. No new stars will flicker to life. No bright blue giants or gentle yellow suns will form. Only the remnants of what once was will remain: white dwarfs, neutron stars, and black holes. These objects will continue to drift through the darkening void, occasionally interacting, but mostly traveling alone. The great stellar cities, galaxies, will persist in form, but no longer in light. Their spark will be gone. Among these remnants, white dwarfs will be the most numerous. These dense, inert stellar cores no longer fuse atoms. They shine only because of residual heat, leftover thermal energy from their former lives. But this heat too will fade. Over trillions and quadrillions of years, white dwarfs will cool, growing dimmer and redder, eventually radiating only in infrared. In time, they will become entirely dark, invisible to even the most sensitive detectors. These fully cooled objects are called black dwarfs. No black dwarfs exist yet. The universe is simply too young. Even the oldest white dwarfs have only had around 13 billion years to cool, not nearly enough time to reach the cold, lightless state of a black dwarf. But in the far future, these dark remnants will dominate the cosmos. No longer stars, but the silent memories of stars. Each one will carry a history of thermonuclear fire, now extinguished, their matter frozen in slow, dense silence. This transition marks a major turning point in the universe's story. For most of its life so far, the cosmos has been lit by starlight, the quiet, ongoing burn of hydrogen into helium. That era is temporary. As the fuel runs out, so too does the light. The skies will go dark, not because something failed, but because the firewood was finite. And once the last embers fade, the universe enters a long night. Not empty, but deeply still. The universe still contains a vast number of stars, roughly 100 billion in our galaxy alone, and likely more than 100 billion galaxies in the observable cosmos. But even this abundance is a snapshot in time. It represents only a moment during the star-rich epoch of the universe. In the far future, this light will fade. According to current models, the last visible stars will burn out roughly 100 trillion years from now, a number that dwarfs the current age of the universe by a factor of more than 7,000. These final stars will not be brilliant giants or blue-eyed beacons. They will be red dwarfs, the smallest and longest-lived stars. Unlike their more massive cousins, red dwarfs burn their hydrogen fuel extremely slowly and do so in a fully convective manner, meaning nearly all of their mass contributes to fusion. Some may live for tens of trillions of years. But even these cosmic slow burners are bound by thermodynamics. Their fuel will run out, and when it does, they will fade gently into darkness. After the last red dwarf cools, the universe will no longer produce visible light. For the first time since stars began to form, there will be no starlight shining anywhere. The night sky will become permanently dark to the human eye. Only faint glows in infrared or radio may persist, and only briefly on cosmic scales. There will be no more sunrises, no constellations, no glowing galaxies. The visual richness of the universe, which has shaped life and guided cultures, will vanish entirely. But this darkness is not emptiness. It is simply the absence of new light. The universe will still contain matter, black dwarfs, neutron stars, black holes, rogue planets, and drifting debris, all scattered sparsely across an ever-expanding sea. These objects will interact occasionally, perhaps merging or falling into black holes, but most will continue in isolation, following the slow gravitational dance of a cosmos that no longer shines. It will be a universe of memory, not creation. In this quiet era, time will take on a different character. Without bright stars to mark days, years, or centuries, the passage of time becomes nearly imperceptible. Cosmic events will unfold not over millions of years, but over trillions and quadrillions. Change will still happen, but so slowly that entire galaxies could drift without incident for longer than the current age of the universe multiplied by 1,000. It is not that time stops, only that activity stretches so thin as to seem eternal. And so the sky, once filled with brilliant constellations and pulsing nebulae, will grow quiet. Not suddenly, but gradually, star by star, light by light. It will become a true night sky, with no dawn to follow. This is not a disaster or a collapse. It is simply the cooling of a once bright system, the gentle exhale of a universe that spent its energy well. And with this final stillness, we move one step closer to understanding what lies at the end of everything. The stars may fade, but matter, the atoms and particles that make up everything, does not simply vanish with them. Once the last lights go out, what remains is not nothingness, but structure, the durable remnants of atoms, compressed cores of stars, and drifting cosmic debris. And yet, even matter itself may not be eternal. Over long enough timescales, the very stability of the proton, one of the universe's most fundamental building blocks, comes into question. Protons are stable on timescales far longer than the age of the universe. We have never observed a proton decay. In fact, if protons do decay, their half-life must be at least 10 to the power of 34 years, more than 100 trillion years. But some grand unified theories of particle physics predict that protons are not immortal. They may eventually break down into lighter particles, such as positrons and neutrinos, through rare quantum processes. This decay, if real, would mark a turning point for matter. If protons decay, then every atom in the universe is doomed to disintegrate, given enough time. Atoms are built around protons and neutrons, which form their nuclei. Electrons orbit these nuclei, held in place by electric charge. But once the proton disappears, the atom unravels. Molecules lose coherence. Structures dissolve. Even the cold, solid remnants of long-dead stars would eventually fall apart into a thin mist of radiation and light particles, drifting alone through the dark. This process would be extraordinarily slow. In the early stages of the Degenerate era, matter would still appear solid and unchanging. But as trillions upon trillions of years pass, individual protons would begin to decay. Entire white dwarfs and neutron stars, once seemingly eternal, would crumble into radiation. Even planets and interstellar debris would disintegrate. It would not be sudden nor dramatic, just a slow thinning of matter, an unraveling of everything once built. But what if protons do not decay? Then matter, at least in its degenerate forms, may persist indefinitely. Atoms would remain bound, even if they no longer participate in chemistry or energy exchange. White dwarfs and neutron stars might remain frozen and inert, lasting into eternity. The decay of structure would be limited not by particle instability, but by rare quantum events, like tunneling or collisions. Even so, change would come, just on deeper timescales than we can currently grasp. In either case, the direction is clear. The complexity of matter is slowly erased. Whether by proton decay or the cold quiet of frozen atoms, the universe loses its structures one by one. There is no rebuilding, no new stars or galaxies. The fabric of matter, once vibrant with chemistry and life, becomes still, flat, and featureless. And though particles may persist, the forms they once built will not. In this way, the death of matter is not an event, but a deep, unhurried transformation. Even before the last protons decay, if they ever do, matter will have undergone profound changes. As stars die and their remnants cool, they leave behind exotic forms of matter known as degenerate matter. In white dwarfs, this takes the form of electron-degenerate material, where gravity is countered by quantum pressure from tightly packed electrons. In neutron stars, it is neutron-degenerate matter, a superdense fluid of neutrons pressed into place by immense gravitational forces. These forms of matter are stable, but only under extreme conditions. Degenerate matter is strange by any normal standard. It has no familiar structure, no atomic lattices or chemical bonds. In a white dwarf, atoms are crushed so tightly that their electrons form a quantum gas, resisting further compression. In a neutron star, the boundaries between individual nuclei dissolve, creating a sea of neutrons. These objects do not shine, but they hold the last organized structures of matter in the far future universe. And yet, even these exotic forms are not immune to change. Over unimaginable stretches of time, the heavy nuclei within degenerate matter may undergo radioactive decay. Isotopes with long half-lives, like uranium or thorium, decay steadily even today. But in the far future, attention turns to nuclei, with half-lives far longer than the current age of the universe. These might take trillions or quadrillions of years to decay, but eventually they will. As this decay unfolds, the already inert remnants of stars become increasingly diffuse and fragile. They lose mass, structure, and energy, not all at once, but grain by grain. Some theories even suggest that in the deep future, unusual atomic structures could emerge. One of the strangest possibilities is the formation of positronium, a short-lived atom made of an electron and its antimatter counterpart, a positron. In the cold, low-energy environment of a far future universe, such structures might form briefly from residual particles. But positronium is unstable. It annihilates quickly, releasing energy in the form of gamma rays. These emissions, while real, would be faint and fleeting, like sparks in an ocean of stillness. Quantum tunneling introduces another layer of decay. Even if particles or structures are stable in the classical sense, they may still vanish through quantum processes that defy ordinary barriers. A black dwarf, for instance, may undergo nuclear fusion via tunneling, despite being far colder than any star. It is possible, though not confirmed, that such objects could slowly convert their matter into energy in rare, spontaneous flashes. These would be the final instances of fusion in the universe, occurring in objects so dark and cold that they have no visible light. But these events would be vanishingly rare, spaced out over trillions upon trillions of years. For the most part, degenerate matter simply endures. It cools, it decays, it quiets, and eventually it disappears. Whether through radioactive decay, proton decay, or quantum tunneling, the organized forms of matter fade from the universe. What remains are particles and radiation, the raw components of everything that once was, now unbound, unstructured, and adrift in the expanding void. Black holes are often imagined as eternal, regions of space-time so dense that nothing can escape their gravity. And for most of cosmic history, they are the last to fade. As stars collapse, black holes become the gravitational anchors of the universe. They absorb matter, grow through mergers, and remain long after light has vanished and atoms have decayed. But even black holes are not completely permanent. According to quantum theory, they slowly radiate away their mass in a process known as Hawking radiation. Proposed by Stephen Hawking in the 1970s, this mechanism arises from quantum fluctuations near the event horizon, the boundary beyond which nothing escapes. In empty space, particle-antiparticle pairs are constantly forming and annihilating. Near a black hole, one of these particles may fall in, while the other escapes. To an outside observer, it appears that the black hole is emitting radiation. This process is incredibly slow, but it means that black holes lose mass over time. They shrink, and eventually they vanish. For a stellar mass black hole, this evaporation takes around 10 to the power of 67 years, far longer than the time needed for stars to die or matter to decay. For supermassive black holes, the timescales stretch even further, to 10 to the power of 100 years or more. But given enough time, even the largest black holes will fade. In their final moments, they will release a brief flash of high-energy radiation before disappearing entirely. This may be the last visible event in the history of the universe. What follows this final disappearance is something deeper than darkness. It is not merely the absence of stars or matter, but the absence of structure. A universe without black holes is a universe without gravitational centers, no points of density, no formations, no edges. All that remains is the physical vacuum, a space that is not truly empty, but filled with the lowest possible energy state allowed by quantum fields. This vacuum is uniform, isotropic, and incredibly quiet. Yet even this nothingness is not nothing in the strictest sense. The vacuum has properties. It contains virtual particles. It has a ground state energy. It can influence the expansion of space through phenomena like dark energy. But it contains no usable energy, no gradients, no change. It is a stillness that supports existence without activity. Philosophically, it challenges our notions of what it means for something to be. In physics, it is the end state of all processes, not a place, but a condition. And so, after the last black hole evaporates, the universe becomes a sea of near-perfect emptiness. No stars, no atoms, no motion. Only particles and radiation spread thin across an endless void. The matter that once formed planets, people, and galaxies is now dissolved, disassembled, and untraceable. The stage remains, but the play has ended. What was once dynamic has gone quiet. And in this quiet, the fate of matter reaches its final chapter, not destruction, but dispersal into silence. Black holes begin their lives as endings. They are formed from the collapse of massive stars, when gravity overwhelms all other forces and compresses matter into an infinitely dense point. This core collapse marks the death of the star, but for the black hole, it is just the beginning. Black holes do not shine, but they grow. Given access to matter, they can become the most massive single objects in the universe, and in their growth, they shape the fate of galaxies. The primary way black holes grow is through accretion, the slow, steady consumption of nearby gas, dust, and stars. As matter falls in, it forms an accretion disk, heating up and radiating energy before crossing the event horizon. In the early universe, black holes had ample access to fuel. Galaxies were dense and turbulent, rich with gas. Supermassive black holes, often found at galactic centers, grew rapidly during these chaotic epochs, sometimes reaching billions of solar masses within just a few 100 million years. Mergers are another pathway to growth. When galaxies collide, a common event in cosmic history, their central black holes often spiral toward one another and eventually coalesce. These black hole mergers release gravitational waves, ripples in spacetime that carry away energy and momentum, allowing the two singularities to join. Over time, this process creates fewer but more massive black holes. Each merger reduces the number of black holes but increases their mass. It is a consolidation of gravitational structure. Yet this growth has a limit. As the universe expands and galaxies move apart, the opportunities for mergers and accretion diminish. The supply of infilling matter dwindles. Stars drift too far to be captured. Gas becomes too diffuse. Eventually, most black holes will become gravitationally isolated, no longer part of dynamic galactic cores, but drifting alone through the vast, empty dark. Without matter to consume, they become dormant. They still curve spacetime, but they interact with nothing. This era of black hole starvation marks a transition from the active, luminous cosmos of the past to the silent, enduring universe of the future. The accretion disks vanish. The gravitational encounters cease. Black holes, once fed by chaos, become inert. They persist because there is little to challenge them. But they also fade from the cosmic stage, playing no role in creating new light, new stars, or new structures. They become quiet witnesses to a universe that is slowly running out of activity. And so, the black holes that once shaped galaxies and bent the orbits of stars will drift alone. For trillions of years, they may remain undisturbed, massive, dark, and patient. They are the last large-scale structures left intact, long after the galaxies have dimmed and the stars have died. But even their stillness is temporary. A deeper process is waiting, governed not by gravity, but by quantum mechanics. And it is through this process that even black holes must eventually fade. The silence of an isolated black hole may seem final, but it hides a quiet process unfolding at the edge of physics. Even in perfect darkness, a black hole is not completely still. It radiates faintly, invisibly, and incredibly slowly through a process known as Hawking radiation. Though black holes trap everything that crosses their event horizon, quantum mechanics ensures that no region of space is truly empty. In the vacuum near the event horizon, particles continuously flicker into existence and vanish. Occasionally, one of these virtual particles escapes, while its partner falls into the black hole. From the outside, it appears as though the black hole has emitted a real particle, and in doing so, has lost a tiny bit of mass. This process is known as Hawking radiation, and it occurs for all black holes, regardless of size. But the rate is inversely proportional to mass. The larger the black hole, the slower it radiates. For a stellar mass black hole, the rate is negligible. For a supermassive black hole, it is nearly zero. Still, Hawking radiation never fully stops. Given enough time, far longer than the age of the universe, even the most massive black holes will shrink. The process begins imperceptibly, unfolding over durations that exceed 10 to the power of 100 years. During this time, black holes remain massive and stable, but the slow leak of quantum particles continues. They lose energy bit by bit, their mass reducing at a pace so slow that it escapes all current detection. But as they shrink, the process accelerates. Near the end of a black hole's life, its mass becomes small enough that Hawking radiation increases rapidly. In the final moments, the black hole releases a burst of high-energy particles, gamma rays, electrons, neutrinos, a final whisper of energy before vanishing completely. No trace is left behind. The event horizon disappears, and the curved region of spacetime it defined returns to the flat vacuum. It is not an explosion, but a release, a final exhale after eons of silence. This marks more than the disappearance of an object. It represents the loss of the last gravitational anchors in the universe. Black holes are the most concentrated sources of mass and gravity. Their existence organizes space around them. When they evaporate, that organizing influence fades. The cosmos becomes flatter, less curved, more uniform. Without stars, without galaxies, and now without black holes, the large-scale structure of the universe dissolves into a sea of weakly interacting particles. In this way, black hole evaporation is not only the end of a thing, but the end of shape. It signals the conclusion of curvature, mass, and structure. What was once a dynamic cosmos filled with gravitational wells and luminous objects becomes a vast, nearly empty field. Space no longer clings to anything. Time continues to pass, but it has nothing to act upon. The last traces of mass are gone. What remains is emptiness, deep, wide, and quiet, beyond imagining. As black holes evaporate, a profound question emerges, one that touches the core of physics itself. What happens to the information that fell inside? According to quantum mechanics, information about a physical system can never be completely lost. Yet black holes seem to do exactly that. Anything that crosses the event horizon becomes inaccessible. When the black hole eventually evaporates, the information it held appears to vanish, defying the rules of quantum theory. This is the heart of the black hole information paradox. Physicists have debated this problem for decades. Some propose that information is somehow encoded in the Hawking radiation itself, spread out in patterns too subtle to detect. Others suggest that information may be stored in correlations at the event horizon, a concept known as the holographic principle. There are even ideas that black holes retain a remnant of Planck scale mass, where information could be preserved indefinitely. But no resolution has been universally accepted. It remains one of the great open questions in theoretical physics. Thermodynamics adds another layer of mystery. Black holes have entropy proportional to the surface area of their event horizons. They also have temperature, the basis of Hawking radiation. As they evaporate, their entropy decreases, which seems to contradict the second law of thermodynamics. But if the outgoing radiation carries away entropy, and potentially information, then the law may still hold. Understanding how thermodynamics and quantum mechanics coexist at the edge of a black hole could be key to a deeper theory of everything. When the last black hole dies, the universe enters a new phase, one devoid of complex structure. No gravitational centers remain. No fusion, no collapse, no organized matter. Just radiation, neutrinos, and a thin fog of particles dispersed across incomprehensible distances. These particles do not interact meaningfully. They simply drift, separated by vast expanses of cold space. The cosmos has no gradients, no engines, no light. It becomes a diffuse echo of its former self. In this state, the universe is as close to equilibrium as it can get. Entropy is maximized. Temperature is uniform. The vacuum energy that drives cosmic expansion remains, but no systems remain to be powered by it. There is no time in the human sense, no change, no motion, no clocks. The arrow of time still points forward, but it moves through stillness. The cosmos continues to expand, not into anything, but simply becoming more dilute, more even, more flat. And what remains after all this? Possibly nothing but quantum fields, stretched thin. Perhaps a few last particles that resist decay. Perhaps a background of faint radiation, too diffuse to ever be harnessed. Or perhaps the vacuum itself, the most minimal version of existence, remains as the final canvas. It is not an end with a bang, or even a sigh. It is a settling into something that cannot age, because it can no longer change. A place where the universe, having spent its energy well, finally rests. Even as matter fades and black holes vanish, space itself continues to evolve. The universe is not expanding into something. It is space itself that is stretching, growing, thinning. This expansion has been ongoing since the Big Bang, but it has not been uniform in speed. For the first few billion years, gravity slowed the expansion, pulling matter together. Then, something changed. Around 5 billion years ago, the expansion began to accelerate, driven by a mysterious force known as dark energy. Dark energy is not well understood, but its effects are visible. It acts as a repulsive pressure, causing galaxies to move away from one another at increasing speed. The more space there is, the more dark energy seems to emerge, accelerating the process further. Unlike gravity, which pulls things together, dark energy stretches them apart. As a result, the large-scale structure of the universe is becoming more diffuse. Galaxies that were once visible will soon recede beyond our reach. This leads to the concept of a cosmic event horizon, a boundary beyond which light will never reach us, no matter how long we wait. As space expands faster than light can travel, entire regions of the universe slip away forever. These galaxies are not moving through space faster than light. Rather, the space between us and them is growing so quickly that no signal can bridge the gap. In the far future, only a few neighboring galaxies will remain visible, everything else fading into undetectable silence. As the expansion continues, this horizon grows more profound. Eventually, even within our local region, the distances between objects will stretch so dramatically that communication and interaction become impossible. Stars, black holes, and particles will still exist, but they will be isolated by the sheer size of space. Every point in the universe will become an island, surrounded by an ocean of vacuum that no ship of light can ever cross. The Hubble constant, which describes the rate of expansion, may not remain constant forever. Some theories suggest it could stabilize, while others allow for it to evolve over time. If dark energy is a cosmological constant, a fixed energy density of the vacuum, then expansion will proceed steadily. But if it is something dynamic, like a slowly changing field, the future could hold surprises. Still, all observations to date point toward continued acceleration. The universe is not just growing, but racing outward faster and faster. This relentless stretching does not tear objects apart, at least not yet. Galaxies, stars, and atoms remain bound by gravity and the strong nuclear force. But on the largest scales, spacetime is uncoupling from itself. Structure no longer forms. Gravity no longer clumps matter into stars and galaxies. The expansion is not chaotic. It is smooth, steady, and quiet, a transformation not of content, but of context. The canvas of the universe is being pulled wider with every passing moment. The expansion of the universe is often described using a quantity called the scale factor. This is a measure of how distances between unbound objects in the universe change over time. When the scale factor doubles, all intergalactic distances have doubled. Since the Big Bang, the scale factor has grown enormously, and under the influence of dark energy, it is increasing faster with each passing epoch. This growth doesn't add matter, but it spreads what exists across an ever larger stage. As the scale factor grows, everything not gravitationally bound becomes more remote. Galaxies that once shared causal contact now drift too far apart to exchange even a photon. The rate at which space expands between these regions outpaces the speed of light, not because matter is moving that fast, but because space itself stretches. Over time, the observable universe, the sphere of everything we can possibly detect, shrinks, not in actual size, but in meaningful content. Less and less of the cosmos remains accessible. The implications of this are subtle but profound. When the observable universe was young, it contained nearly the entire cosmos. Today, much of what exists has already moved beyond our event horizon. In the future, observers, if any remain, will see only the closest remnants of structure. To them, the universe will appear static, dark, and local. The signs of expansion will be erased from view, not because they've stopped, but because they've receded beyond visibility. This process leads to what physicists call asymptotic flatness. As matter thins and structure fades, the geometry of the universe approaches perfect uniformity. Space becomes smoother, more isotropic, less warped by the presence of mass. Without large gravitational distortions, the curvature of spacetime flattens. The dynamic fabric of the cosmos settles into simplicity. Every region becomes like every other, not identical in detail, but indistinguishable in behavior. The universe loses contrast, becoming a vast, empty symmetry. At this point, the rate of change itself slows dramatically. There are no new stars forming, no significant structures evolving, no visible interactions occurring. The particles that remain continue to move, but their paths are unaffected by others. Entropy has erased the sharp features of the universe. What once was a turbulent dance of gravity and radiation becomes a tranquil drift through emptiness. Not because time has stopped, but because nothing is left to mark its passing. And so, the universe becomes quiet, not just in light or motion, but in curvature. The great stretches of space-time, once warped by galaxies and black holes, lie nearly undisturbed. The stage is still present, but its players are gone. What remains is the frame of the cosmos itself, expanding, stretching, and smoothing into simplicity. As we move forward, we'll explore what this final geometry might look like, and whether even space-time, at its limit, has a fate of its own. As the universe expands and empties, it moves closer to a state known in cosmology as de sitter space. This is a theoretical solution to Einstein's field equations, a model of a universe dominated entirely by vacuum energy, where matter and radiation are absent and space expands exponentially forever. De sitter space is smooth, symmetric, and nearly featureless. It is not a region of destruction, but of infinite stillness, a kind of cosmic plateau beyond which change becomes meaningless. In de sitter space, the expansion is not chaotic or unstable. It is uniform and unending. Every region grows at the same exponential rate. From any given point, the universe appears to have a horizon, a boundary beyond which light will never arrive. But this boundary is not an edge. It is a consequence of acceleration. Like standing in fog that thickens with distance, the horizon exists not because of obstruction, but because of expansion that always stays ahead of you. The cosmos stretches faster than information can travel. Even in this smooth geometry, thermodynamics still applies. De sitter space has an associated temperature and entropy, though extremely low. The horizon that forms in an accelerating universe carries entropy, a measure of the information hidden beyond reach. This entropy is finite and fixed for a given value of the cosmological constant. It suggests that even the vacuum has a thermodynamic ceiling, a maximum number of possible quantum states that space can contain. Once this ceiling is reached, no further change is possible. This limit introduces a kind of heat death, not just of matter, but of space-time itself. In a traditional heat death, particles are evenly distributed, and no energy differences remain to drive change. In de sitter space, this applies to geometry. The curvature of space no longer evolves. The expansion continues, but it no longer carries information or enables new structure. It becomes pure background, a space-time that exists, but does not do. Quantum fluctuations may still occur in de sitter space, but they are random, unstructured, and lacking in persistence. The vacuum may occasionally twitch, creating brief bursts of virtual particles. But with no gravity to bind them, and no structure to hold them together, these fluctuations cannot build anything lasting. The horizon prevents coordination, and the entropy limit prevents novelty. The universe has not stopped existing, but it has lost the ability to express itself. This is the far end of the cosmic arrow, not a singularity or collapse, but an approach to stillness so deep that even the fabric of spacetime ceases to evolve. The future becomes an endless present. The equations still hold, but they describe a universe that has run out of stories. And as we look toward the last steps in this journey, we are left to ask, what happens when time itself no longer has a reason to pass? Time, as we understand it, is inseparable from change. We recognize time's passage by observing events, a star igniting, a planet orbiting, a particle decaying. These transitions mark the forward motion of existence. But as the universe becomes empty and still, the number of such transitions dwindles. In the far reaches of Degenerate space, change becomes so infrequent and so meaningless that time itself begins to dissolve as a useful concept. It is not that time stops, but that it no longer measures anything. In everyday physics, time is a coordinate, part of the fabric of spacetime. It allows us to order events and calculate durations. But when events vanish, when no clocks tick and no systems evolve, the difference between one moment and the next becomes purely abstract. If nothing changes between now and 1 trillion years from now, is there truly a difference? The mathematical arrow of time may persist, but its experiential content fades. This raises deep questions in both physics and philosophy. In thermodynamics, time's arrow is tied to entropy, the forward drift from lower to higher disorder. But in the ultimate heat death, entropy is already maximized. There are no more gradients, no more energy flows. The entropy remains constant, and so does everything else. Without entropy change, time has no thermodynamic direction. The universe is not cycling or collapsing. It is simply existing in a single, vast, static state. In general relativity, time can bend, stretch, or even loop under extreme conditions. But in Degenerate space, these possibilities fade. The geometry of the universe becomes fixed. Expansion continues, but nothing happens within it. There are no clocks, no observers, no reference points. Every location becomes indistinguishable from every other. Time continues to be defined mathematically, but not physically. It becomes a parameter in an equation with no terms left to evaluate. Some theorists suggest that in this limit, time may effectively evaporate from the physical description of reality. If no interactions remain and no observers exist to mark time's passage, then the concept of time may become unnecessary or even meaningless. The universe would not end in destruction, but in silence. It would not be frozen, because freezing implies motion halted. Instead, it would be empty, a condition so stable that nothing remains to distinguish one moment from the next. And so, the end of space-time is not an event. It is a horizon of stillness. The universe does not crash into a wall or collapse into itself. It simply loses the capacity to evolve. Expansion continues indefinitely, but carries no change, no energy, no future. The fabric remains, but the pattern fades. It is a kind of immortality, without memory, without story. A cosmos that has reached the far edge of becoming, and now simply is. The idea of the universe reaching a final, changeless state invites an even deeper question. Can space and time ever truly end? If nothing changes, does the fabric of spacetime continue to exist? Or is there a deeper boundary, not of space, but of meaning, beyond which the very concept of existence dissolves. Physicists tread carefully here because the tools of science rely on observation, and a perfectly still cosmos offers nothing new to observe. In classical cosmology, space and time are assumed to be eternal backdrops. They host events, but are not events themselves. Yet modern physics increasingly views spacetime as emergent, a property that arises from more fundamental relationships, like quantum entanglement or thermodynamic structure. If that's the case, then when those relationships vanish, the fabric they create may vanish too. Spacetime may not persist in the absence of structure. It may not be a container, but a consequence. Even the emptiest vacuum is not truly nothing. It is a quantum field in its lowest energy state, filled with virtual fluctuations and uncertainty. These subtle features give rise to gravity, mass, and force. If the vacuum loses this structure, if it settles into a truly minimal configuration, then it is possible that the very geometry of spacetime becomes undefined. Without curvature, without particles, without fields in motion, there may be no meaningful coordinates to define. The universe would not collapse, but fade into mathematical invisibility. This leads to speculative frontiers of physics. Could the universe tunnel into a deeper vacuum state? Could time itself fragment or emerge anew under exotic boundary conditions? Or could there be a transition not to a new cosmos, but to a deeper silence, a place where the very grammar of physical law no longer applies? We do not know. Our best theories break down in this regime. The edge of time may not be a moment, but a conceptual threshold. Philosophically, this resembles ancient questions about the void. Is emptiness a thing or the absence of things? Is it a canvas or the lack of canvas? In the deep future, the universe may answer this not with violence or collapse, but with stillness. If no observers remain and no structure persists, the distinction between space and nothingness may blur. There may still be a mathematical universe, a set of coordinates and rules, but nothing within them to play the game. In this way, the fate of space-time may not be destruction, but erasure. Not by force, but by fulfillment. The cosmos may approach a kind of completion, a state where no further change is possible, and so no further physics is needed. Whether this is an end or a beginning depends on what follows, if anything. But in terms of the universe we know, built from fields and forces, space-time and motion, this would be the quietest end of all. In the silence that follows the universe's final acts, a strange kind of possibility remains. Not because of what is present, but because of what is absent. When the universe becomes flat, empty, and still, when it reaches maximum entropy and minimum structure, we are left with a question that stretches beyond physics. Is this truly the end, or simply the quiet before? Something new begins? With no matter, no clocks, and no observers, the universe has no script. But it may still hold potential. Some theories suggest that even in the most silent vacuum, quantum fluctuations could trigger new beginnings. Tiny pockets of space could spontaneously tunnel into lower energy configurations, forming what physicists call bubble universes. These would expand from a point, possibly inflating into entirely new realms of physics, causality, and time. Our own universe may have begun this way, a fluctuation in a prior vacuum driven by conditions we cannot observe. If this process continues, then even in the quietest state, creation has not been silenced. But these ideas remain speculative. The probabilities involved are uncertain. The mechanisms are not yet understood. And if such fluctuations occur, they may be forever disconnected from our universe, their expansion sealed off by cosmic horizons, their timelines unreachable. To us, the parent universe remains unchanged, featureless, and without witness. The new bubble is not a continuation, but an offshoot, sealed in its own causally separate envelope. What emerges from nothing may not relate to anything. And so we are left with two extremes: a universe that has emptied itself into a pure, stable vacuum, and the faint, uncertain possibility that this vacuum contains seeds for other realities. Whether this represents rebirth or finality is unknown. What is clear is that space-time as we know it, curved by mass, shaped by light, measured by change, has vanished. What remains is not lifeless, but formless. Not cold, but changeless. It is the final abstraction of a universe that once burned with stars. Perhaps this is the true asymptote, not just of time or entropy, but of physical possibility. As energy disperses and structure fades, the tools we use to describe the universe begin to lose their meaning. Physics relies on contrast, mass and emptiness, force and resistance, time and motion. When all contrast is erased, what remains is not a broken theory, but a theory with no subject. The universe no longer has something to be about. And yet, there is still wonder in this silence. The idea that everything, stars, galaxies, thoughts, arose from a brief span of ordered motion within a much longer sea of quiet is humbling. It reminds us that the dynamic universe we now see is a moment, not a norm. That space-time, like life, may be temporary. And that perhaps, in the stillness beyond, something waits. Not something new, but the unshaped canvas from which all things once began. Among the many proposed endings for the universe, one stands apart for its simplicity and inevitability: heat death. This scenario is not violent or sudden. It does not involve collapse or explosion. Instead, it is the quiet settling of everything into maximum entropy, a state where all usable energy has been exhausted, and no further work can be done. The universe continues to exist, but it no longer evolves. No new stars form, no black holes accrete, no atoms bind or break. It is the final equilibrium. To understand heat death, we must return to the second law of thermodynamics. In any closed system, entropy increases over time. Energy spreads from concentrated forms to more diffuse ones. Heat flows from hot regions to cold ones until all regions reach the same temperature. When this happens on a cosmic scale, all gradients vanish. Every part of the universe becomes thermally uniform. The temperature may be close to absolute zero, but not perfectly so, just cold enough that nothing meaningful moves. In this state, particles still exist. Photons continue to travel. But because there are no differences in temperature or density, there is no motion that can be harnessed to create change. No energy can be extracted to build or power systems. The universe is not destroyed, it is done. Time continues, but without events. Space expands, but without consequence. Matter exists, but without interaction. It is not emptiness, but stillness, a universe that has gone as far as it can go. This scenario does not contradict the laws of physics. In fact, it follows directly from them. Every process we observe, from the burning of stars to the mixing of air in a room, increases entropy. Given enough time, the total entropy of the universe must reach a maximum. And when it does, there is nothing more for the universe to do. The lights go out, not from catastrophe, but from completion. The cosmos becomes a resting system. One of the striking features of heat death is its permanence. Once entropy is maximized, it cannot decrease. the universe cannot spontaneously become ordered again. There is no reverse flow of heat, no undoing of the expansion. Even if regions fluctuate briefly, as quantum theory allows, they are limited in scale and duration. Nothing complex, lasting, or structured can arise again. It is a horizon beyond which no story continues. This vision of the end is haunting in its quietness. There is no collapse, no external boundary, no moment of conclusion. Just a deep, stretching quiet, where galaxies once burned, where particles once collided, where time once marked change. All that remains is distance, silence, and the gentle hum of equilibrium. In this version of the universe, the end is not an event. It is a temperature. And when that temperature is everywhere, the universe has reached its final form. Closely related to heat death, but often described with its own name, is the scenario known as the Big Freeze. While heat death emphasizes entropy and thermodynamic equilibrium, the Big Freeze focuses on the relentless expansion and cooling of the universe. It describes a cosmos that grows colder and more dilute with time, not because it runs out of energy, but because that energy becomes so spread out that it is no longer usable. In both cases, the outcome is similar, but the emphasis differs. The Big Freeze begins with the same observations that support modern cosmology. Galaxies are moving apart, space is expanding, and that expansion is accelerating. If this acceleration continues unchecked, the distances between galaxies will grow so great that they will no longer be able to interact. Even within galaxies, stars will fade and black holes will evaporate. Eventually, all matter will be too far apart to exert gravitational influence. The universe will not just be cold, it will be lonely. In this vision, the cosmos stretches indefinitely. There is no limit to how far space can expand. Every particle drifts farther from every other. Over time, the density of the universe drops ever closer to zero. Even photons, particles of light, become so redshifted by the stretching of space that they carry almost no energy. Light becomes undetectable. Motion ceases not because the laws of physics have changed, but because the universe has removed every condition needed to sustain motion. One of the defining features of the Big Freeze is that it does not require any new physics. It follows from what we already know: the properties of dark energy, the conservation of mass energy, the dynamics of an accelerating metric. It is a quiet prediction, not based on a dramatic endpoint, but on the continuation of current trends. If nothing interrupts the expansion, and if dark energy remains constant, then the Big Freeze becomes not just likely, but inevitable. In contrast to the heat death's focus on entropy, the Big Freeze is more about geometry. The universe does not just cool, it becomes infinitely wide. The horizon of causality collapses inward. Even light, which once connected distant galaxies, becomes trapped in isolated pockets of curved space. Time continues to pass, but no signals are exchanged. The universe becomes a collection of disconnected regions, each adrift in a sea of silence, unable to share information with any other. To observers, if any could survive long enough to see it, the Big Freeze would feel like a cosmic withdrawal. First, the galaxies disappear, then the stars fade, then the warmth of particles becomes imperceptible. In the end, space would feel both endless and empty, a place where the canvas stretches forever, but nothing remains to draw upon it. And in that vast quiet, the universe would reach not a climax, but a drifting away, a long, cold exhale into the infinite. While the Big Freeze and heat death describe a quiet fading of the cosmos, the Big Rip envisions something much more violent, a universe that doesn't drift into stillness, but accelerates into disintegration. This scenario arises from a particular form of dark energy known as phantom energy, which would cause the expansion of the universe to speed up at an ever-increasing rate. If this form of dark energy exists, then not only will galaxies move apart, but the very fabric of space-time may eventually tear. In the standard model of cosmology, dark energy acts like a constant repulsive force, causing space to expand steadily over time. But in the Big Rip scenario, that repulsion becomes stronger as space stretches, a feedback loop where expansion fuels more expansion. Unlike a gentle acceleration, this process would become exponential and ultimately unstoppable. Structures held together by gravity, electromagnetism, and even the strong nuclear force would all eventually be pulled apart. The timeline of a Big Rip depends on the properties of phantom energy, which are not yet confirmed. If this energy exists and behaves as theorized, the first signs of destruction would come billions of years from now. Galaxies would separate beyond communication. Then, a few 100 million years before the end, galaxy clusters would disband. Planets would drift from stars. In the final minutes, stars themselves would be torn apart. In the last fractions of a second, atoms would be ripped open, nuclei disassembled, and even the vacuum of space would become unstable. At the moment of the Big Rip, space-time would cease to be continuous. The laws of physics, which rely on coherent coordinates and stable fields, would collapse. There would be no time, no space, no matter. The entire structure of the universe would dissolve into a singularity of expansion, not a point of infinite density like the Big Bang, but a final state of infinite stretching. Nothing survives, because nothing can hold together. The very threads of existence are unspooled. This scenario is highly speculative. It depends on the existence of a particular kind of dark energy that has not been observed. Current measurements suggest the universe's expansion is accelerating, but we do not yet know if that acceleration will increase forever, slow down, or stabilize. Still, the Big Rip remains within the bounds of physical theory, and it serves as a powerful reminder. The fate of everything may depend not on the matter we see, but on the dark forces we barely understand. Whether or not it occurs, the Big Rip offers a dramatic counterpoint to more passive endings. It suggests that the universe's end might not be silence, but rupture, not a fade, but a break. A cosmos that spends billions of years building stars, galaxies, and life may, in its final moment, become too vast to bear its own structure. It is a future not of cooling, but of unraveling. And if it comes to pass, it will be the swiftest and most complete end of all. One of the strangest and most quietly ominous scenarios in modern cosmology is the possibility of vacuum decay. In this view, the universe as we know it may not reside in the lowest possible energy state of space. Instead, it may be suspended in what physicists call a false vacuum, a metastable state that feels stable from the inside, but could be replaced by a more stable configuration if a quantum transition occurs. If this happens, the result would not be evolution, it would be total transformation. To understand this, imagine the vacuum of space not as empty, but as a field, with a certain amount of energy embedded in its structure. That energy defines how particles behave, how forces interact, and even how space-time curves. But in quantum field theory, a field can sometimes rest in a local minimum, like a marble resting in a dent on a hillside, rather than the absolute bottom. If a lower state exists, and the marble tunnels through the barrier, it will roll down and settle there, changing the landscape entirely. Applied to the universe, this means that the vacuum itself could fall to a more stable energy state through a process called quantum tunneling. Such an event would create a bubble of true vacuum, expanding at nearly the speed of light. Inside this bubble, the laws of physics would be different. Particles would have different masses, forces could change in strength, and chemistry as we know it might cease to exist. Nothing from the old universe would survive. The bubble would sweep outward, rewriting space itself. Crucially, this would happen without warning. Because the bubble expands at light speed, we would not see it coming. There would be no time to react, no signs to interpret. One instant, the universe would appear stable. The next, its fundamental structure would be gone. Vacuum decay is not a slow process. It is instantaneous on the cosmic scale, a phase transition not of matter, but of existence. It is not violent in the classical sense, but it is absolute. The possibility of vacuum decay is grounded in high-energy physics. The mass of the Higgs boson measured in recent years suggests that the current vacuum is indeed metastable, though only barely. This does not mean decay is likely or even imminent. The timescale may be longer than the lifetime of black holes, longer than the entire future age of the cosmos. Or it may never happen at all. But it remains a mathematically valid outcome, lurking in the equations that describe our universe's foundations. What makes vacuum decay so unsettling is its finality. It offers no aftermath, no debris, no future. It does not stretch space or cool matter. It erases the stage entirely, replacing it with something else, something we cannot imagine, because we are made of the laws it would destroy. And yet, despite its severity, it is not a failure of the universe. It is simply one more way that quantum fields might evolve. Not an ending in time, but a change in being. Not every model of the universe's fate leads to silence or destruction. Some theories suggest that the cosmos may be part of a grander cycle, one in which expansion gives way to collapse and death gives way to rebirth. These ideas fall under the umbrella of cyclic cosmology, where the universe does not have a singular beginning or final end, but instead oscillates between phases of growth and contraction, forever rewriting itself in endless loops of time. The oldest version of this idea is the Big Crunch, in which the expansion of the universe eventually slows, stops, and reverses. Galaxies would begin to fall back toward one another. Clusters would merge, temperatures would rise, and the universe would collapse inward, eventually returning to a state of extreme density, perhaps similar to the conditions of the Big Bang. From there, a new expansion could begin. This would not be a sequel to our universe, but a full reset, a fresh beginning from the ruins of the last. However, observations of dark energy and accelerated expansion make a true Big Crunch unlikely under current physics. If dark energy continues to dominate, the universe will not contract. It will accelerate forever. But other models have adapted. Some suggest that the cosmos could still bounce, not because gravity pulls it inward, but because of deeper quantum or geometric processes that cause spacetime to recycle itself. These versions of the theory propose that a bounce could occur even in an ever-expanding space. In one such theory, the ekpyrotic model, the universe we observe is just one phase in a series of collisions between higher dimensional spaces. Each collision produces a new Big Bang, expanding into a fresh cosmos with different initial conditions. In these models, time stretches infinitely in both directions. There was no first universe, and there may be no last. The cosmos breathes, expanding and contracting, each cycle separated by a kind of cosmic heartbeat. Other cyclic models involve entropy resets. Since the second law of thermodynamics demands that entropy must increase, these theories suggest that some mechanism, perhaps at the point of collapse, resets the entropy level, allowing a new universe to emerge in a low B. Entropy state. The physics of such a reset is not fully understood and may require quantum gravity or string theory to explain. But if true, it would allow the universe to begin again without violating known thermodynamic principles. Cyclic cosmologies are attractive not just for their elegance, but for their ability to sidestep the finality of heat death or vacuum decay. They suggest that the cosmos is not a story with a last page, but a rhythm with no final beat. Whether by quantum bounce, brain collision, or geometric reset, the universe would continually reawaken, not as a repetition, but as a renewal. Each cycle would be unique, yet connected. And in this way, the universe would never truly end. It would begin again. After tracing so many possible futures, the cooling stillness of heat death, the infinite drift of the big freeze, the violent unraveling of the big rip, the sudden transformation of vacuum decay, and the breath-like renewal of cyclic models, we are left with a quieter question. Will the universe truly end? Or is that a concept shaped by human experience, applied to something that was never meant to follow our patterns of beginning, middle, and end? In ordinary life, endings are tied to narrative. A star burns out, a book closes, a lifetime passes. But the universe may not fit so neatly into such frames. Time, at the largest scales, is not a story, but a dimension. It does not know closure. Many of the endings we've explored are not events, but limits, asymptotic horizons approached but never reached. The universe does not fall silent in a single moment. It simply becomes more quiet, more diffuse, more settled, until nothing meaningful remains to unfold. This gradual unwinding challenges our sense of what it means to conclude. If the cosmos still expands, still contains particles, still holds quantum fields, is that truly an end? Or is it simply a different mode of being, where complexity has faded, but existence continues? Perhaps the universe in its later stages becomes not dead, but still. Not finished, but featureless. The tools of physics still apply, but their subjects have left the stage. Even in the more abrupt scenarios, such as the big rip or vacuum decay, the word end may be misleading. These events do not destroy the idea of a universe. They replace one with another, a new spacetime, a new geometry, a new set of possibilities that we cannot predict. In that sense, they are not finalities, but transitions beyond our frame of reference. What ends, perhaps, is not the universe, but the rules by which we once understood it. And there is another possibility, that the question of endings is incomplete, that the cosmos is part of something larger, a multiverse, a deeper quantum framework, or a system of laws that generates not one reality, but many. In that view, our universe may end, but existence continues, not in a sequel, but in parallel. Other realms, other histories, other versions of physical law may persist, independent of our own. And what feels like an end here may be nothing more than a page turned elsewhere. In the end, or perhaps we should say, at the edge, we are left with silence, not as a cessation, but as a condition. The universe may not end in drama or collapse. It may not even end at all. It may simply evolve beyond structure, beyond change, beyond time as we know it. Whether that stillness is an ending or a threshold depends not on the stars, but on the questions we choose to ask. And so, with the last of the hypothetical futures behind us, we are ready to drift into quiet reflection. And so, the stars have faded, the galaxies have wandered into darkness, and the deep fabric of space itself has stretched toward stillness. What once burned brightly now rests in silence. Not gone, not broken, only quiet. Time, having carried the universe through its bright beginning and long unfolding, slows its breath. There are no more clocks here. No pulses of light. No gravity wells or spinning clouds. Only distance. Only presence. The universe does not mourn its stillness. It does not need noise to be whole. It simply becomes what it must become. And perhaps, in that quiet, there is something beautiful, a kind of completion that does not require understanding, a kind of peace that exists without asking why. You, listening now, are part of that same long journey, made of atoms forged in stars, drifting on a planet still warm with light. And while you rest, the universe continues to unfold. Not quickly, not loudly, but with the patience of forever. So if you find yourself letting go, if your thoughts begin to drift, let them. There is no need to stay awake for the end of the universe. It has no end you can miss. It simply fades, like breath on glass, like the last ripple on a still pond, like the hush after the final word is spoken. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.